Hi guys, today we are going to be looking at circle theorem, and what we're going to do, we're going to be looking at a typical CSEC question. I know for many of you this is a sore spot, so what we'll do, we will start with a typical CSEC question, and we'll be looking at the number 10 question on the CSEC 2017 paper, circle theorem. For many of you, once you see this, moving right along, but not after today. Hopefully you will be able to target one of these questions a little better. So take your time, look at it for a second or two. Everybody can see? Right, just look at it for a little while, and then we're going to move as to how we're going to target a question like this. Okay? All right, what we're going to do, we are going to take this CSEC question and we're going to reconstruct it here, meaning that I'm going to redraw that same thing here. And you're maybe saying, but Miss, why would you want to redraw? You'll see in a while how redrawing, reconstructing the question actually helps you to target it better. Before we do that, we need to be able to label a typical circle, all right? So let's label a typical circle. If you go here, I'm sure most of you can see this is a radius, good. This is the diameter, all right? What the diameter does, it cuts the circle into two halves, very good. Or we can call them, yes, I heard that, semicircles, very good. So if we cut a circle into half, that means we are using a diameter to get two semicircles. Now, there's the center of the circle here, and most times it is denoted just by a 0, okay? So once you see the 0 or the O, it means that this is the center of the circle. Any line coming from the center of the circle to the circumference, as you can see outside here, is called a radius, all right? So we have a radius, which means that the radius is half of the diameter. Very good, okay? Or you need two radii, R-A-D-I-I, two radii to form a diameter. Good. Then we have here a chord that is any line going from the circumference to circumference here. But the marked difference between a chord and a diameter is that the chord does not go through the center, all right? So you can have a chord anywhere else. If it goes through the center, it's a diameter, all right? Good. So those are the main things that we need to know. Oh yes, and the arc. Okay, arc is part of the circumference. It is part of the circumference. So what you need to know when you're labeling the circle, especially for circle theorem, would be things like the radius, the center, diameter, chord, arc, circumference. Put in segment here, which does not really apply to our question for today. Tangent also, but those are just things that you need to know for further reference and other circle theorem. Okay, so we're good on that, everybody? All right, good. So what I'm going to do, I am going to reconstruct our CSEC question right here. I'm going to put in the center. What letter demarks the center again? Yes? O, very good. O demarks the center. That's the center of my circle. I'm going to put in a line here. What is that line? It comes from the center to the circumference. What's that line? Radius. Good. I'm going to put in another line. What is this? Another radius. Good. So I have two radii. Nice. I'm going to put in a line here now. What's that line called? A chord. Very good. So what I've done, I've actually put in two radii and a chord. What have I formed, if you look at that? Everybody can see that it's a triangle. Very good. But most specifically, what kind of triangle is that? Isosceles is correct. Why is it isosceles? Because we know that an isosceles triangle has two equal sides. How do we know that it's equal? How can we be sure it's equal? Because they are two radii, and in all of my life, I've never seen a circle with two different radius. Have you? No. All right, so if this is a radius and this is also a radius, it makes these two lengths equal. So if these two lengths are equal, these two angles are also equal. And although This in itself is not a circle theorem. It is a concept in geometry that is imported into circle theorem, okay? So many teachers, they don't teach or many people rather, they don't teach the isosceles as a theorem, but it is there, it is tested. So you have to look out for that every time, okay? So we have this isosceles triangle within the circle. So if this is an isosceles triangle, these two things are equal. These two angles rather are equal. All right, let's just see how that applies to circle theorem. Let's say I were to make this angle here 120 degrees. What is the size of one of those angles? Miss, how are we going to do that? To do that, the first thing you have to know is that all the angles in a triangle going to add up to 180 degrees. Very good. All the angles in a triangle, when you add them up, must add up to 180 degrees. So if you already have this one at 120, what you will do, you will say 180, take away 120, and that's going to leave you with 60 degrees. So does that mean that this is 60? One of them is 60? No, cannot be. They both together have to give you 60. So the next step would be to divide by 2. And so each of these angles here would be 30 degrees. All right. So when you add that up, 120 and 30, 150 plus 30, that's 180. All right. So the isosceles triangle theorem here makes these two angles equal because those two lengths are equal because those two lengths are radii. Good. All right, so we have that down. All right, the isosceles triangle right there in the circle. Good. So we have one little part down. Let's look at what CSEC does next. Follow with me. Oops. This one comes here. All right, starting to look more like our question. Yes, right. So here's what they did. They extended this up here. So look at this. This line here has extended to the center of the circle, and we have it at 120. This one here goes up here. I want you to think with me for a minute. Let's say these were two angles running a race. They started at this point here, and this point is what? A chord. Very good. So two angles, they're starting a race, and they're starting at the chord, all right? So this one comes up to the center. So we can safely say that it has run half of the race and conserved more energy, so it's at 120. What happens to this one? This one runs the entire race, the entire course. So let's go again. They start here. This one stops at the center. It's 120. This one here runs the entire course. So that means it has conserved less energy than this one, right? Because this one only ran half of the race. So if this one is at 120, can somebody make a good guess and tell me what you think this angle would be here? 60 degrees. Excellent. Excellent, because this one has run half the race and that one ran the full race, all right? So that's 60. Please, guys, don't go telling anybody that I say angles run race and conserve energy, lest they arrest me for mathematical heresy. We're just saying here that the angle at the center is going to be twice the size of the angle at the circumference once they come from the same chord or the same arc, all right? So once two angles come from the same chord, the one that's at the center is going to be twice the size of the one at the circumference. Get that? So that's theorem number 1 we're looking at today, and I'll repeat. The angle at the center will be twice the size of the angle at the circumference once they come from the same chord or the same arc. Are we clear on that? Good. All right. So we're going to look at the, okay, before that, let me just tease you a little bit. So if this one was 50, what is this one? This one would have to be twice this one. Very good. So this one would have to be 100. Awesome. If this one, let's say, was 200, how much would this one have to be? This one is twice this one, so it would have to be 100. Excellent. We're doing good. All right? Good. Nice. So we're closer to what the CSEC question looks like. Let's do the last part, and here's what I'm going to do. Here and here. Okay? So what we have essentially done, we have 4 points. I'll call this A, I'll call this B, I'll call this C, and I'll call this D. What we have here is 4 points on the circumference, okay? 4 points within the circle forming a quadrilateral, but all 4 points are touching the circumference. And this is what is called a cyclic, whatever part of the country you come from. You will decide how you pronounce it. Cyclic or cyclic quadrilateral, okay? And what that means is that it is a 4-sided shape that all 4 points touch the circumference, okay? Now, what is interesting about that? Why do you need to know that? The most essential thing about this is that the opposite angles in cyclic quadrilaterals are supplementary. Simply mean they add up to 180, okay? If I can just redraw something quickly for you so you can see. All right, so we have our 4 points touching the circumference. 1, 2, 3, 4. All right. So I just said that this is called a cyclic or cyclic quadrilateral, and the important thing about it is that all opposite angles are supplementary or they add up to 180. So I'll just label in the opposite angles. This one here is opposite to this one. This one here is opposite to this one. So if this one, for whatever reason, is 60 degrees, how much would this one be? Remembering that they're supplementary, they add up to 180. So it would be 180 minus 60. This one would be 120. Very good. And for whatever reason, if this one is 100, how much would this one be? Quick math. 80 degrees. Good. So basically, that's what we've done. We've looked at the 3 main concepts that governs this question that we have been looking at, the CSEC questions. So let's just recap what we've looked at today. We've looked at 3 theorems, okay? The first one, like I said, is not essentially a circle theorem, but it is a geometrical concept that is imported into circle theorem, all right? So what we have here is that the isosceles triangle, and like I said here, made up of 2 radii. So we are sure it is isosceles because there are 2 radii making 2 lengths equal, therefore 2 angles equal. Good? And then we have the angle at the center, which is twice the one at the circumference, since they're coming from the same arc, or what word can we insert here? Arc or chord. Very good. All right. So that is the second one. And the last one we looked at is the cyclic quadrilateral, where opposite angles are supplementary. All right. So those are the 3 that are going to govern this particular question. Remember, I'm saying this particular question because essentially there are more than 3 circle theorems. In total, there are about 10 of them, all right? But what we did today, we did one question which had only 3 theorems, okay? So what I would like you to do at home is to look at the other theorems and try to reconstruct them the same way I did here, all right? Try and redraw them. Obviously, in the exam, you're not going to have time to redraw them. But if at home you're accustomed of redrawing them, it makes it easier for you to spot the concepts that are involved in those questions. Like here, while restructuring this, I realized, like, whoa, these are 2 radii that has to be put in here, and so it formed the isosceles. I noticed that that was the chord that I was putting in here, so that was the chord that was the base for those 2 angles here, all right? So as you restructure, then the concepts come to life a little bit more, all right? So go through your theorems and try and restructure them. Even use CSEC questions as well, and restructure them, redraw them, so you can get a better understanding as to what's going on here. All right, guys. Okay, so when I come back, I am going to actually go back to our CSEC question. We'll review the theorems. We'll go back to our CSEC questions and see how we can attain full marks on the circle theorem. Promise me that you're not going to just run through the theorem or just skip it next time. All right? Good. We'll see you in a bit.